The next session for the afternoon, and we're going to keep looking at some experimental results, and Wenlu is going to present some of the real cutting-edge characterization techniques. And so your title is Physical Properties of Partially Molten Rocks from Microtomography Experiments and Digital Rock Physics. So, Wenlu.
Thank you. When I was looking at the program, the first thing I was wondering was, what is the frog's view from Dave's title? Now I understand, so it looks like I'm another frog in this crowd, and we're going to look at really micro scale. And this work is mostly done by my former PhD student, Kevin Miller, who is right now a postdoc in Stanford University, and my other collaborators, including Laurent Montesi, University of Maryland, and Glenn Gaetani in Woods-Hole Oceanographic Institution. Okay, so I thank Dave for a very comprehensive introduction. Now I don't have to talk too much about partially molten regions on Earth. So this talk, we are concentrating, focusing on the porous flow part of the partially molten region below the mid-ocean ridges. All right. So showing here is one of the East Pacific rise, the fastest spreading ridges, and in 1998. Led by Don Forsyth at Brown University, they did a seismic and electromagnetic tomography experiments, and they find that to model the seismic observations as well as the EM data, you can basically use 1 to 2% of partial melt. Doesn't need much any heterogeneity, and you can model the data pretty well. So this is the starting point of our experiments, 1 to 2% of melt. So the question is, with this, if it is porous flow down there, and with 1 to 2% of melt, how fast the melt can rise? And that obviously has quite significant bearing to the, for example, chemistry of basalt, all right? So for really long time that we already understand that the partially molten rocks is like in the metallurgy literature, that you have a fluid phase and a solid phase. And in that case, Von Bargen and Wolf did a finite element model showing that if you have isotropic, homogeneous, uniform grain size, as one word, the simplest system, then you can derive that relationship between the permeability and the melt fraction. And this is the parallel relationship that everybody is referring at. And then then later on, based on experimental works and other observations, for example, in analog system, this is the work done by Work and Watson using the quartz and water, and they basically can reproduce some of the parallel relations. But direct measurements of permeability on partially molten rocks is very challenging because first there's a high pressure temperature, then melt is really viscous. When you actually need to drive the melt, you need to apply quite large of a differential pressure. This large differential pressure can deform the rock, so it's a combined hydraulic and rheology problem. So in that case, that for a long time we use microstructure to infer the permeability, and so if you take the partially molten permeability, let's say it has 1 to 2% melt with the mantle rock peridotite grain size, and give the n equal to 2 or 3, which there's a really nice work by Mike Cheadle in 1989, and he did his PhD basically show that from tubular to sheet-like connectivities, you can have the end changes, right? Then what you get is essentially the permeability estimate will be somewhere like 10 to minus 13 to 10 to minus 11. So this permeability essentially is like normal sandstone with 20% of porosity or very clean sand, right? That type of permeability. But if you put that and use a really simple analog to say, hey, the buoyancy-driven melt is lighter than its surrounding mantles, and then how much is the melt ascent velocity, you get somewhere around 50 centimeter per year, and that would roughly correspond to an extraction time of over 100,000 years. And for a lot of geochemists, if you look at the data, that's too slow. So one of the things that people has been done for a really long time is to say the weak link here is the permeability. We don't know how reliable this parallel relationship would be and what should be the power. And so we decided that to take a detailed look. So this is what I call the procedure for digital rock physics, because doing the actual measurement in the lab of permeability of direct partially molten rocks is hard, right? So what we did was we used the piston cylinder, and we take the San Carlos olivine, just like every other experimentalist study the mantle rock. That's our starting point, with mixing with different melt fractions. And then we take the cores and do it with the synchrotron based X-ray tomography. The reason we use a synchrotron is in synchrotron you can use monochromatic beam. All right, with a monochromatic beam, the lights were highly cohesive, so that you can actually do a lot of edge-enhanced techniques to enhance the phase difference. That is because the melt, basaltic melt especially, and the olivine, if you just look at their density contrast, it's not that much, so that a lot of time the resolution is not that high. So after that, once you get the image, you select a representative volume and segment melt from its solid, and then after that, you essentially have a digital rock that has a representative 3D microstructures. And then you can use this to simulate a process, right? In this case, we simulate the process by adding pressure gradient to the digital rock, so you can conduct a virtual experiments to calculate the permeability and the electroconductivity. And you can also get all kinds of statistical analysis of the rock based on 3D structure. So in this case, the first set of experiments we did was having the starting material that is San Carlos olivine and basaltic melt, so that's why it is called SCOBA. So San Carlos olivine plus basalt, right? So with 20, 10, 5, and 2% of morb mixture, and then we put it in the piston cylinder and cook it at 1.5 GPa and 1350 C, and quench it and drill the cylindrical cores for microtomography study. And this study was done in advanced photon source in Argonne, Illinois, and the annulled samples is less than 1 millimeter in diameter, so that we can achieve the maximum pixel resolution, which is in this case 0.65 micron. All right, that's about 700 nanometer. And once you get that, you can do the image processing. The first thing is to remove noise and artifacts from the original data. And one of the things we find is that the anisotropic diffusion filter is really important because that's what, unlike the usual Gaussian filtering, that these preserve the edge the best. And because of the contrast between the olivine and the melt are small, so we rely on the edge to tell the two phases apart. And once you have that clean set of filtered data, you can then assign the segmentation process. You assign different values. In this case, it's a two-phase, so 1 is melt, 0 is olivine, all right? Then you basically can conduct all the analysis you want. So first thing we did was we tried to make everything simple so that the idea is we wanted to have a textural equilibrium so that the melt distribution would represent, in our case, more in the static mantle, right? And so you can see that the grain size distribution in these cases, right, is evolving as this is 42 hours of annealing and 84, 168, and 300 something hours, like 2 weeks, right? And you start to see a characteristic a grain size distribution, and yes.
You have the same distribution with the normalized grain size? Because if I understood grain size distribution correctly, you have to normalize it to a time-independent grain size, which would be the mean, mode, or median grain size. And so in that case, the distribution doesn't look necessarily the same as if you're plotting it to an equivalent diameter.
I basically follow this is one of the paper that's Uli and who is sitting there, and his students working on, and in one of this paper, and we basically follow their procedures and try to look at that characteristic log normal peak.
Because in your paper,
But if it's a log normal distribution, what
Yeah.
it looks like, I mean, that would be consistent. You can plot it not normalized, or you can plot it normalized.
it would have the same.
Yeah, yeah.
Okay.
So with that, I'm showing you one video that shows the 3D distribution. This is the melt phase alone. Olivine wasn't plotted. All right, that's 2%, and then this is 5%, and 10%. And 20%. So what you see really is melt at low 2%, all right? So they mostly concentrate on the triple junctions. And with a higher melt fractions, I call them spill over to the grain boundaries, all right? So with that, then we can conduct this virtual permeability experiment. So now this is a 3D subvolume of that sample, right? And if we add a thin layer of boundary before you get to the pressure gradient, the reason you do that is if you don't do that, then immediately the flow only goes through one or two of the really large ones, all right? So if you want to distribute that without the edge effect, you just add 2 layers of elements, all right? Then they distribute. And then with the pressure high in this end and low in that end, you're going to drive the flow. And with that drive flow, you can actually calculate the flow velocity. All right, so you see now the flow basically goes through that microstructure. You see where the high velocity channels are and the low velocity channels are, all right? And with this, obviously, you can also calculate how much volumetric flux is, and using Darcy's law, you can get the permeability. And obviously, because this is a virtual experiment, you can give the viscosity of your likings, and so that's overcome some of the actual experiments problems. So this is a more systematic data that Kevin conducted, that he took different regions and tried to find out what will be a representative large enough subvolume, all right? So each one of these boxes are increasing by size, and then you calculate the permeability and see they start to converge, all right? And then that's the largest size we use. To use this, obviously, if you use the whole volume, first, the computation time is really long. Secondly, is that then what you get is a average melt fraction. Whereas with localized subvolumes, if they're enough, then you actually, there's always heterogeneity. So you actually can squeeze one sample, you actually can have a range of porosity difference. Say, if you put 5% in regions, you may have 3%, and the other regions, you may have 6%, all right? So that's to our advantage. And then this is the calculations. So you see that at 20% sample, you have some variations from the regions, and the 10%, 5%, and 2%, you go almost as low as 1%, all right? So with this each one of this is the calculation. The permeability, because this is computed, all right, there isn't much of an uncertainty to talk about. But with the porosity, so what we did is because our resolution is by pixel, all right? So at 1 pixel, you could basically not being able to tell this is actually a melt or an olivine. So what we did was, if you basically assume this pixel is completely melt, then that's a lower end of olivine and a higher end of melt. And then if you assume this pixel of boundary is completely solid, that is the lower end of the melt volume, all right? So that's why each one of them has the uncertainty. But you can see that even with the uncertainty, you can essentially fit a nice power law in this log-log scale. It's a linear relationship, and that's how the Dave referred to us very graciously. That's the n equal to 2.6. But the caveat here is it's 1% to 20%, right? Below 1%, the microtomography cannot resolve the melt channels, all right? We don't have data. And that actually is really nicely corroborated by Connolly's study in 2009, when they actually conducted experiments by putting the partially molten San Carlos olivine and basalt and spin it, right? With the spinning, they use the centrifugal force to redistribute the melt. And then afterwards, they look at the redistribution of the melt and infer the permeability porosity relationship. They get actually relatively not as accurate of n, but their C is corresponds to what we get rather nicely. All right, we get about 30 and they get 27. That's remarkable in the sense that this is a completely different system, different imaging system, and so on. So I think for that, it is quite robust. And then the good thing about the virtual experiment is you can conduct electroconductivity on the same sample without a sample-to-sample variation, all right? So we did also now using the same rock, and now instead of putting the pressure gradient, if you put a voltage gradient, impose the voltage gradient, you're going to drive a electroconductivity through, all right? So we assign the olivine conductivity. In this case, even if it is less conductive than melt, it's still conductive. And those are numbers from literature. And we assigned the basaltic melt conductivity as 7.53. And now if you apply Ohm's law, you can calculate the bulk electrical conductivity. This is important because in experiments, we actually can measure electroconductivity. And because it's hard to measure permeability, but measure conductivity is actually feasible, a lot of people try to use the electroconductivity measurement to infer permeability measurement. But you need to ground truth that. So what we see is this, that our result, this is a log-log plot of conductivity versus the measured melt fractions, right? This is all the dots are where we calculate the electroconductivity, and you can also fit a power law there. But this actually has a similar shape, but has some of the absolute value discrepancies from one of the measurements by Tengrohius, right, in 2005. What we see is that in our data, the simulation result fall right between the Hutchins-Strickman upper bound and the lower bound, whereas the experimental data is actually more consistent or even above the Hutchins-Strickman upper bound. So with two-phase mixing, that doesn't really make a lot of sense to us, but these seem to be robust for a few electrical conductivity measurements. So what we think happening might be, first, what we take in our virtual experiment is that the olevine's conductivity and melt conductivity are completely dry conductivity, all right? And in the experiment, those are actual ones. So even if they are dry, they may be nominally dry. So we don't know how much of a water content is there. So we put both water in the melt and the water in the olivine just to see what's going to happen. And once you have the water in the melt and the olivine, there will be a partition based on melt. So we use that melt program to calculate how much that will affect it, and those are the numbers we put there, right? So if you use just the dry simulation, this is what it is. And if you put different water fugacity in the melt, then you start to, wet melt is more conductive, then our value can go up. And then you see that this can cover some of the range of the measurements. And if you have dry melt but have the olivine, well, it's not completely dry because there's a system. So if you put water in the olivine, they will go on to the melt also, right? So that basically is looking like this. And because this shape seems to also changes a little bit, so we think that it's probably there's still a little more water in the melt in the actual experiment. But at any rate, these also, yes?
Perhaps a thought. In a real experiment, wouldn't the, maybe not, I'm thinking about partial melting. In the experiment, would the water content, because of the partitioning between melt and solid of the water, I was wondering if experiments with different melt contents would have different concentrations of water.
Yes, that's.
So you have to connect different dots on your numerical experiment. Is that right?
Right. We use the melt program to basically try to estimate that, but obviously the actual one might be slightly different too.
What was the material in the experiments? Was it again San Carlos?
Yes,
Olive?
we have
Was that
other.
always wet?
Right. We have other experiments, but those are not exactly always San Carlos and Morb, so that we only refer that's Tengrohius results here. But there are other results from Robert and Taberti and also Japanese group, Yoshida and et al. Right? So there are more of those measurements. But I think that one of the cool thing about this virtual experiment is that you can now have the same rock and you can conduct permeability and electroconductivity around the same rock, all right? And then you can look at the flow path versus the current path. And so this actually shows that because of the electric flux, the dependence of the hydraulic radius and the fluid flux dependence are different, all right? So they are sensitive to the hydraulic flux. Is sensitive to, more sensitive to the size of the hydraulic radius than the electrical ones. So now you see that if these are same structures, all right? This is the current, this is the flow, all right? So water is blue and current is hot, all right? So that's why this is red and that's blue. And the really blue ones are the main very high flux regions, all right? This is a high current. But what you see is even though there is a melt conduit, all right, for permeability, it doesn't contribute much at all right? Whereas for conductivity, it does, all right? So I'm just zooming in and these features are everywhere, okay?
What's the melt fraction?
In this case, it's 5%, all right? Then we can, from this set of data, basically measure the path tortuosity, right? So in here, you see that the tortuosity for the flow, which is blue, that's a fluid, and the tortuosity with the current, all right? They are different. And now what's interesting thing is you also see that they are even more different in the high melt. In our case, the high melt fractions. That is because, remember, there's a spillover. And then you have the thin green boundary melt. With those be more prevalent in that network. So you get, they are sensitive, the electroconductivity are still sensitive to it, but the permeability are not sensitive to the green boundary films.
How do you define, or how do you quantify tortuosity here?
Basically, you follow the flow path, right, and then you have the sample length, right, from one end to the other, and now you get the tortuosity. It's L over L.
But is that some sort of ensemble average?
Yes.
Okay.
Yes. All right. So now I like to say the take-home message from this virtual experiment is that if you want to link the permeability from the conductivity measurement, all right, then what you need to really beware of is it's usually there is going to be no generalized relationship applied to all. You may, if the system is less heterogeneous, right, you may have a better chance to do that than when it is highly heterogeneous, right? And especially when the flow path changes a lot, right? For example, the hydraulic radius changes a lot. So you need to basically try to satisfy as much as the implicit assumption that the flow path is more or less the same with the electroconductivity, the current path. Otherwise, to infer one from the other is going to be giving you a very large error. All right? So the next set of experiment is that we started with a simple system that's olivine plus basalt. But as Dave has really nicely introduced to us that the mantle is much more complex and with a lot of heterogeneities. So in this case, we're only going to do a little bit more is how about Hartsbergite? So for a petrology jargon is that if we call peridotite, that's dominantly just olivine as a solid phase. And whereas if you add orthoparoxene, OPX, then the higher percent of OPX gives you the Hartsbergite. So if we now say, hey, adding the OPX to the mix, because OPX actually have a different wetting behavior, then what does that do to affect the conductivity and permeability? So this is the second set of experiments we did. And in this case, we use about 60% of olivine and 40% of OPX. And these are not from grinding materials. We actually do them starting mixture of oxide. All right, so then with that, we then mix with, in this case, about 4% of basalt in this particular case. All right, so what you see is that we have the olivine grains, you have the melt, and then you have the OPX. You probably already start to see that these shadow zones seem to be more melt dry than the olivine rich zone, all right? So what we're going to do is to quantify that. And these are the set of sample that we use the oxide mixture from the bulk composition given by Dick's 1977 paper from the southwestern Indian Ridge Hartsbergite. And I have a detailed list of how much each one of the MgO, CaO stuff that I'm not listing here, but it's published in our paper. And then to produce a 60 to 40 volume ratio of olivine to OPX, and the melt fraction again is 2%, 5%, 10%, and 20%. Again, this is a piston cylinder experiment so at 1.5 GPa and 1350. And for all of this is about 168 hours, and we did also time series for that, only 5% melt. And then we did the X-ray tomography with the same resolution, and this is what we get. Now the challenge is that not only you have to separate the melt phase from the solid phase, you also need to separate the olivine from the OPX. The olivine to OPX has even more challenging, and we were very lucky to work with the beamline scientists who actually continuously trying to push the boundary and be able to tell. And one thing you actually realize that in the X-ray image, right, the denser phase is always brighter. It's opposite to the SEM image that Dave shows. Right? So our olivine is a brighter, lighter gray, and the OPX is darker gray, and the melt is appear to be more black. Right? If we have a pore here, in this case I didn't show, then that's like whole, like really, really black. Okay? And so here shows how we do the segmentation and ground truthing. All right, so the one thing is that the X-ray is going to have really hard time to detect the dry boundary, all right, because there isn't much of a difference between them for you to detect that. So the dry boundary usually is really hard. So in that, we have to refer some of the program to interpret that's a olivine. So there can be uncertainties in that grain size, all right? But if the boundary is wet, right, at a melt percent that's higher than our resolution, then we can tell the grains and the grain boundary. So the melt can be easily tell apart, the orange, right? And the olivine and the OPX, if we can also tell, but if there's just an olivine to olivine dry boundary without melt film, then the boundary, you have to take a grain of salt. All right, so with that, we compute the permeability too of the Hartsburgite sample, compare with the peridotite sample. Remember, the peridotite one is the blue now, all right? And the new one, the Hartsburgite, are the red. The one thing, to our surprise, I was expecting to see some difference adding OPX. To my surprise, that's up to 3%. There isn't a measurable difference of the permeability between the Hartsburgite and the peridotite. But below that, we actually find, for example, one of this one that's around 1% of melt, the overall melt. And we didn't see, we calculated permeability and it come out 0, because if you look at it, there's no thoroughgoing percolation network, right? So essentially the melt are being isolated, all right? So with Greg Hirth, that's I have done a network model before, basically to mix the olivine and the OPX, and I built a network with a geometry of a tetracadahedron, and so that we do a Monte Carlo mixing, just to say through 60% of olivine with this wetting angle, through 40% of OPX with that wetting angle, and then calculate the permeability. In this case, all grain sizes are uniform, right? Everything is just controlled by the dihedral angle. What we find is that above 40% of OPX, right, you have very significant loss of the melt conductivity. That is, the OPX wetting is above 60, right? So now below 3%, you start to basically, they just form little balls and they don't connect to each other, right? But if the OPX up to, I'm sorry, wrong button. But if the OPX is above 40%, you don't see much of the difference. This above 40%, we don't see much difference. But we clearly start to see that this difference, right? So one thing is, yes, we confirmed that above 40%, the model predicted there should be some difference. We don't see that small difference. Second, that even below 40%, we start to see a drop off, whereas the model predicted that you need to be higher than 40%. So we think this has something to do with because in the model we predict is just a strict 1+1 mixing. There's no interaction between the melt and the melt redistribution. So what we think happening is a melt redistribution, which is a large part of my talk, in that we also calculate electrical conductivity, and you see the conductivity actually changes a little bit, has a measurable change. And if I want to really put a fit there, the N changes from 1.3 to 1.9 by adding the OPX. So what causes the no change? You're adding 40% of OPX, right? Above 3% of melt, you actually don't have any change in permeability. So we think that comes from this really nice paper from Bruce Watson in 1999. So what's there, based on Park and Young's model, They basically say, hey, different materials, all right, with different wetting behavior. If you look at the total system energy for the high wetting angle, like 75 degrees in this case, all right, the system actually wants to have less melt. The system prefer to be dry to stay low in total energy, all right? And whereas with the low dihedral angle, the system prefer to be wet to reduce the energy. So if you put these two together, and even though the input melt fraction is, say, 5%, when it sees OPX, right, OPX does not get 5% because the system sees olivine, and the olivine prefer to have more melt so that the system's energy will get lower. So this was termed by Bruce called, this is a lithological partitioning because of the focusing comes from the difference from lithology. So this shows the idea the total energy would be the solid and the liquid, and it depends on how much of melt you put there, okay, then you're going to have less of some phases as melt associated with it, more with the other phases that melt goes with it, all right? So he did, actually on analog system, fluoride and quartz, all right, to put them sit next to each other with the same porosity and in this case with the pore fluids of distilled water. And after you wait for 2 weeks, you see the fluoride, they started the same porosity, but after 2 weeks, the fluoride basically has much less of water than the quartz. And this basically is driven by the interfacial energy, right? He also did OPX olivine with the olivine sit next to OPX, but then after a week, you don't see much of a statistical difference in melt fraction in the OPX and olivine. So he says that's because the morb is so viscous. You probably have to wait a lot longer, maybe a year or something, to see a significant difference. So then we said, we actually have this data, and in our case, the olivine grains is sitting right next to the OPX grains. So the melt actually doesn't have to travel millimeter or centimeter distance. They travel micron distance. And then we wait for 160 hours comparable to this. Maybe we'll see something different. So this is what then Kevin did, and we are about to submit this paper, is that to characterize the local melt fractions associated with each grains, right? It's a really time-consuming work, but he did a really good job that first to characterize the local melt fraction is not that easy, because if you look at that picture, how much of the melt you say is belong to this grain versus its neighbor's grain, right? So for that, it's already hard, but we talked about it, and by and large, he figured one way to do it. And basically, we start with a ellipsoid fitting a grain, all right? Then we grow that ellipsoid. So when you start with the ellipsoid just fitting the grain, they essentially have very little melt associated with it. You now expanding that, then you start to have more melt, all right? So we are basically plotting the melt associated with that grain as a function of the ellipsoid size. So at some point, you will see that if it is too small, you're not having any melt on the boundary. But if it is too large, you're including melt from your neighbors. So there has to be an optimal size. We let the program decide what will be the optimal size that you can say this is the melt associated with the grain. Obviously, this would not work unless you do a lot of grains. Each one of them make 1,000 grains, all right? That's why only a PhD student can do this. The best work always done by PhD students. So this is what we get. So in this case, he did about 1,100 grains, all right? What he plot is with the OPX associated with the OPX and associated with olivine. And you start to see they start not very different, so they end not very different because this is too large a region and too small a region, but they always come up with some peak at the size of around 1.1 to 1.4 of the original grain size, all right? And he then used that difference as an indicator of the melt redistribution. All right, so we see quite consistent, and then this is what essentially you plot, have all these thousands of grains, and then do the averaging, and so this would be the ratio between the melt associated with olivine divided by melt associated with OPX, and you see the most of them we see is always above 1, so more melt associated with olivine than OPX. Guaranteed, there's quite a bit of fluctuations from those rocks because these ones are each individual grains and then you do the average, all right? But then you plot them against the melt fraction, this is what you get. So they, given the range of the jumps, and we basically, one thing I think comes up is, yes, there are more melt that's associated with olivine than the OPX. I think that's robust. And if you really want me to put a number, say how much more, all right, I would put somewhere around 1.4, 1.3. That's the ratio.
This is all with 40% OPX.
This is always 40% OPX. We now have another suite that has 20% OPX. We didn't go higher yet because I was heavily influenced by my oceanographic colleagues that you don't have evidence of more than 40% of OPX. All right, so with this, I like to summarize and say why this is important. And now I realize I don't even need to talk about this because Dave already talked about this. All right, yes, in the melt transport, the channel must be dominant, even though these channels are not resolvable right now by seismic data. All right, so this shows the Danite channel. And there are two right now melt focusing mechanisms. Dave talked both of them. The reaction infiltration instability, the RII, and the deformation stress-induced melt segregations. Right? Both of them were observed at the grain scale or aggregate scale from Dave's lab. Then what we show here is it could also driven by interfacial energy. So in places, let's say when it's beginning, when there is absence of pressure gradient or shear stress, right? So one first thing is adding the OPX does not necessarily reduce permeability. It's actually with these focusing mechanisms, the permeability is not reduced by the OPX, right? Another thing is these might be operating, well, this, at least in our case, operating at the different scale. So that redistribution can provide one of the feedback to those large scale mechanisms. So with that, I'm going to conclude. So I like to say that using the microtomography, we did, in a lot of sense, confirm some of the already people's hunch about what's happening in the permeability. But so basically provide a quantitative constraint on permeability, electroconductivity, and also show that how when you try to relate permeability and electroconductivity, you ought to be careful in understanding how they network, the heterogeneity of the network. And then once you add another solid phase, and the lithological melt partitioning should be considered. And this partitioning at higher melt fractions, because they push it to the olivine, it's actually have less impact on the permeability. But with low melt fractions, they act as they choke off for the melt channels. So they do two things. For high melt fractions, then it enhances the permeability than expected. But for low melt fractions, it can completely make the cutoff permeability higher than otherwise. I will stop there. Thank you.
Questions? Vivian.
Did you look at all at the anisotropy of the permeability tensor?
Yes, the permeability was calculated as a tensor, and we don't for the both the Hartsburg samples and the prototype samples, we didn't see much of the anisotropy.
Yeah.
One of the pictures you showed had zoning in the olivines.
Yeah.
What is the cause of that?
I don't know. I am.
It looked to me as if the iron was distributing into the melt from the olivines, but it was all really very small scale, so it presumably is strongly time dependent.
Yes, I agree. I don't know. We are trying to do more analysis, and we think that's why we were thinking about with the partitioning. So what you do is you are putting the olivine regions become more melt rich, and it's left the OPX region becomes more melt poor, and there's something about that heterogeneity in the permeability, basically, because remember we are also growing those things, makes it less, I don't know, homogenized, or I don't know. We did see that they seem to yes, a few grains clustered together.
I mean, on diffusion timescales, how long will it take for that to homogenize by diffusion? I wouldn't have thought very long. If it's an iron magnesium imbalance, which is what it looked like, that the magnesium number that's very, very quickly re-established. So I was very puzzled by that. Clearly you are too.
Yeah. But one thing I can say is that because we do have the just 40 hours, that actually show less of those zonings.
Even more puzzling.
Yeah.
Andrea?
I don't understand very well why, at very low melt fractions, the lithologic partitioning decreases the permeability.
Because the cutoff for OPX, if I take 75 dihedral angle, right, then the back of envelope thing is that it cut off at 5%. And that is a single phase system. With the overall, because we relate that to overall melt, right? So let's say I put 6%, the OPX shouldn't cut off yet. But if you have olivine, the OPX doesn't receive 6% because the olivine actually receive 7%. The OPX only have 4%. So now the OPX are not connecting.
And you think this depends on the OPX fraction in the system? Because if you have only a few patches of OPX, it should not really matter.
They don't have they are homogenized to start with, and they have places that's rich more clusters, but they are thrown out.
So you mentioned that you are in the olivine OPX system. You are growing them from oxides.
Yeah.
So do you see any oxides that are left over and unreacted?
No.
So it's always 100% reactant. Okay.
Yeah.
Because I was wondering if some of these issues you're seeing at very low melt fraction cases, or some of the differences that you're not seeing, could be attributed to oxides.
We didn't see any of that. We actually did some of the microprobe to look at that. We didn't see that. The only thing I can say is that ones that from oxide, the grain size grow faster, like the olivine and the OPX. Then you start with 2 to 5 micron, like the crushing powders, and cook them for the same amount, like 200 hours. They grow from oxides. We have on average 40 to 50 micron of grain size for olivine, whereas for the other ones, like 30.
Yeah, so I have a question. So at some point you started actually detecting the grain boundaries, which is clearly really difficult. But were those included in the electrical conductivity
Yes,
simulation?
as much as we can.
Yeah.
Yeah,
Okay.
yeah. So the only time that we cannot, absolutely not detecting any boundary is it's completely dry and olivine adjacent to an olivine. Even if it's a really small melt fraction that we cannot, it's below our resolution, the ray is still having a phase lag. And that gives us some idea about there's a change. You see a change, right? That's the age-preserving thing. But if it is dry, then we don't see that. So some of that, if that's the case, that will basically take as the whole grain. But that shouldn't change the conductivity, because let's say two dry solid grain adjacent to each other, right? Then you can view that as the same one. So that's the sigma.
Maybe you want to say something.
Yeah, I'm going to re-ask Lars's question.
Yeah.
And what he's getting at is that there is a grain boundary there, dry or wet. It has a higher conductivity by orders of magnitude than the grain interior. So in your finer grain size materials, there may be a conductivity contribution that
Yes.
you have not accounted for. You can't treat those grain boundaries as if that's a single crystal.
So what we did is this. Then we know. So if there's melt, all right, if there is melt, and if we cannot resolve that, so what we did is, what Kevin did is, for every grain boundary, we essentially add 1 pixel of melt. All right? That's why you see this large. They don't change the conductivity very much because it's really thin. Well, our reasoning is, if you have these above 1 pixel, we should start to see some. So maximum. So we try to do a partitioning and say, only fraction of melt. It turns out this computation is really intensive. So we just say, anything we don't see, right, add 1 pixel of melt. You're going to change the conductivity some, but you don't change the relations. And you don't change the permeability at all.
No,
That's
I'm not surprised you don't change the permeability, but you do change the rate at which
Yes.
atoms can diffuse along the boundaries, which
That's
gives rise to
yes, yes. Once you think about the diffusion process, yes, that will. Yeah, absolutely.
I have another one from Rich Katz. He asks, would the conductivity and the permeability scale with grain size in a similar way? Would the ratio give a constraint on grain size if we know permeability independently?
For the conductivity, we did not. Let me put this back. For the, so why don't I put the permeability, we definitely put a grain size there, right? But for the conductivity, there isn't the grain size in the equation, right? So I don't know if they scale the same or differently. You can help me on that.
They can't scale the
Exactly.
same way because
Right.
the conductivity must go essentially as the cross section through the melt, right? And it
Yeah.
doesn't matter how it's distributed.
Right.
Whereas it matters very much how it's distributed
Yeah,
from the point of
permeability.
view of the permeability.
Right.
So the answer is no.
The answer is no.
It seems to me. It's on your head being no.
I'm just saying that you see how the Ohm's law we use to get the conductivity.
Last questions? Okay, why don't we thank Wenlu again.
Thank you.